So welcome to part 3 of lecture 14. In this part, we're going to talk about the roots of a polynomial. So again, this is something that you've probably seen or remember from calculus, and I've actually recalled the definition here. So a number, lambda, is a root or a zero of a polynomial if when you plug that number in, you get 0. Okay, so it's like we're evaluating the polynomial at that particular number. And we do this over and over again in calculus. And many problems in math, uh, uh, reduce to solving roots of a polynomial or some sort of function. Now, this following theorem is something that you probably used over and over again in calculus as well, which says that suppose that you have a polynomial and you have a number, then that number is a root of the polynomial if and only if the polynomial can be factored as z minus that root times some polynomial q. Okay, so in terms of the factorization of the polynomial, you can see the root. And let me give you a proof for why that's true. Okay, so let's take a polynomial, and let's take the polynomial s, which is going to be z minus lambda. Okay, now by the division algorithm, so by the division algorithm, there exists Q and R, so polynomials also with coefficients in my field, such that I can write PZ as Z minus lambda times QZ plus RZ. Okay, and what else do we know? Well, we know that either this polynomial RZ is 0 or the degree of RZ is less than the degree of SZ. Okay. Now, one thing you want to point out though is that this guy here is 1. Okay, because my polynomial s is this element right here. It's a degree 1 polynomial. So the degree of RZ either has to be 0, so it's a constant, or it's 0. Okay. Now, what else do we know? Okay. But we also know that when I stick in 0, sorry, not 0, I stick in lambda into my function, I get 0 because it's a root. So I should get the same thing on both sides, right? I should also get lambda minus lambda, q minus lambda, plus r minus lambda. Okay, and this guy here implies that 0 is equal to r lambda. Okay, now if the degree of rz is 0, then rz is just equal to r, which is inside of f. Okay, so what we have to have here is if r does not equal to 0, then we have that 0, which is equal to r lambda, is equal to r, which doesn't equal to 0. So a contradiction. So what we have is that r actually has to be equal to 0. Okay, but let's think about what that meant then over here is thus our polynomial pz can be factored as z minus lambda times qz, which is exactly what we wanted to prove. Okay, and now let's do the reverse direction. And that direction is a little bit easier, which says that if pz is equal to z minus lambda times qz, then when I stick in lambda into my function, this first term here is just 0, right? And then the second term is whatever the polynomial q is evaluated at lambda, but this is equal to 0. So lambda is a root of the polynomial p, which is what we wanted to show. Okay, and so this is a nice result because we actually see the division algorithm being used inside of our proof. And well, this is something that you would have seen seen in calculus and use all the time, where you're looking at the factorization of your polynomial to find roots. Now, the one thing that you have to be very careful about when you're looking at roots of polynomials is that the existence of roots depends upon which field you're looking at. Okay, and so the classic example of this is the polynomial z squared plus 1, which is equal to 0. And you can rearrange this to having it saying that z squared is equal to -1. And so this has no roots in R. So this is a polynomial with coefficients in R, but it doesn't actually have any roots in R. But on the other hand, it has the roots plus or minus I in the complex numbers. And the fact that the polynomials will have roots depending upon whether you're looking at the real numbers and complex numbers comes into play later on in the course, because when we look at these operators, we get polynomials attached to them, and how those polynomials factor will tell us something about the operators. And how it factors, or its roots, will depend upon the real numbers or the complex numbers. So we'll see results where we actually have to pay attention to where the field is, and the reason we need that is because of the existence of roots. And in particular, one of the main result differences between the real numbers and the complex numbers comes in the fundamental theorem of algebra. And again, this is something you've probably seen before. It says that if you take any polynomial, and it's a non-constant polynomial of degree m, then p has a unique factorization, okay, up to the order of the factors. So depending on which way you put its linear factors, of the form pz is equal to c times z minus lambda 1, c minus lambda 2, and so on. So you can factor it completely into these degree 1 polynomials, where the condition is that the c and the lambda 1, the lambda 2, they don't need to be distinct. They can be repeated. Okay, it's quite possible that some of them are repeated. So the point of the fundamental theorem of algebra is that every polynomial can be factored into products of the form z minus a with a inside of c. So you can see all the roots of the polynomial directly from the factorization. Okay, but this, you should notice, is that we really do need the complex numbers here, because it's not true over the real numbers. And the classic example again is the polynomial z squared plus 1. There's no way to factor it as z minus a, z plus b for any a, b, and r. Okay, we can't break this up into smaller polynomials. So any polynomial over c, you can break it up into polynomials of degree 1, but it's no longer true over r. So the question that you may be thinking is, okay, so we have the complex numbers here, we can break it up into linear forms. What can you do if we had r here? And in the last part, I'll quickly explain what you can do when you replace the c with the real numbers.